If you look at the trajectory of artificial intelligence, it's easy to assume the heavy lifting happens entirely on GPUs. We treat the traditional CPU, the chip that runs your laptop, like an obsolete piece of office equipment. But the physical reality of the industry looks very different. Take Microsoft's Fairwater complex, a massive data center campus built specifically to run OpenAI's frontier models. This layout shows what you'd expect: a colossal 295-megawatt building for a massive GPU cluster. But look at the 48-megawatt structure next door. Containing 0 GPUs, it's filled with tens of thousands of CPUs, consuming enough power to run a city. If AI is all about graphics processors, tech giants wouldn't be scrambling to secure these massive CPU allocations. To understand why this hardware is suddenly a bottleneck, we have to trace its evolution. In the 1990s, the first modern servers were essentially just high-powered home PC processors. Companies took chips like the Pentium Pro and repurposed them to handle early web traffic. As the dot-com era boomed, designers solved traffic jams by putting multiple processing cores onto a single chip, allowing them to calculate different tasks in parallel. By the late 2000s, companies stopped buying physical servers and began renting remote space from hyperscalers like Amazon and Microsoft, shifting their hardware costs from upfront capital to monthly operating expenses. This business model was powered by hardware virtualization. Using software called a hypervisor, a single physical CPU could be split into multiple, secure virtual machines, allowing dozens of different customers to run workloads on the same chip at the same time. This efficiency turned compute into a utility, where server cores rarely sought idle. But while the industry optimized the CPU for web traffic, they were inadvertently preparing to sideline it for the next big shift. When ChatGPT launched, the math required for AI upended the data center. Training models requires massive matrix multiplication, a repetitive task perfectly suited for a GPU's thousands of simple cores, rather than a CPU's complex, branchy architecture. The CPU was demoted to a head node role. Its job was reduced to managing the GPUs, feeding them data, and handling basic hosting. Data centers began a process called socket consolidation. They retired millions of older servers and replaced them with a few highly efficient cloud-native CPUs, often at a ratio of 7-to-1, just to free up power for more GPUs. This consolidation made the CPU market look like it was treading water, even as GPUs consumed the industry's entire financial and power budget. But that dynamic is shifting again. Modern AI training has moved past simple math and into reinforcement learning environments. Inside an RL loop, the AI generates code, runs physics simulations, and verifies data to see if it's correct. These tasks require the complex sequential logic that only a high-performance CPU cluster can provide. We're also seeing a spike from agentic AI. These models browse the web and use software tools just like humans do, creating a massive surge in general internet traffic that GPUs cannot process efficiently. Because GPUs are now sitting idle while they wait for CPUs to fetch and verify data, the CPU has once again become the critical bottleneck for AI scaling. Training runs consume hundreds of megawatts, hitting a physical wall in how fast data can move. Solving this bottleneck requires a complete redesign of data center layouts to prioritize inter-chip communication. The modern infrastructure is a symbiotic cluster, massive arrays of GPUs linked directly to advanced CPU clusters to keep the training loop running at full speed. This triggered a new race between silicon giants. Intel is prioritizing wafers for its server-grade Xeons, while AMD is aggressively taking market share with its Venice and Turin chips. Hyperscalers are also designing their own custom hardware. Amazon has Graviton, Microsoft has Cobalt, and Google has Axion, all designed to bypass traditional x86 logic for better efficiency. Physical infrastructure companies are tying it all together. NVIDIA dominates the networking, while Supermicro and Dell build the specialized racks that house these interconnected processors. By 2026, AI performance is as much a result of physical rack density as it is neural architecture. The same basic silicon logic that once powered a 90s desktop has returned as the primary gatekeeper for the next generation of intelligence.